Hello, everybody. In this video, I will go through the least square solution type of questions. I will do two questions on this context. This is related to week 4, week 5 of the course Linear Algebra, Maths2501, Maths2099 at University of New South Wales. Now, the least square solution of ax is equal to y, basically, this is a very general format that I put here as an information. A is a matrix, P rows, Q columns, and the y is a vector in the p-dimensional vector space. We would like to find out the minimizing the vector x. We would like to find out x vector such that the minimizing the distance between ax is equal to y is a solution to the normal equation A transpose ax is equal to A transpose y. And the columns of A are linearly independent. If they are linearly independent, then the solution is unique. Otherwise, they need not to be unique. The vector x is called the least square solution of the equation ax is equal to y. The idea is that basically the A, uh, you have a data. And in this data is all over the places. Think about that. You have a time. When the time is changing, your data is changing over the time. And you would like to find the simplest form. You would like to find, if you think about your data can be expressed as a pair in two-dimensional space, like x and y points. This is the simplest version. Usually the data, but if you understand this, you will be able to understand the larger set of the data. This basic idea that is used in the least square solution that I'm going to talk about today is really the basic idea for the big data sets. That's called the regression method in the larger sense of the data. You have many data and you find out the connections between those data. It's called the regression analysis. The basic idea is gives you that path to go through the regression analysis, actually, and it's a pretty large area. So you have basically the data. Imagine that you have XY points that you can dot. You can think of the X as a time and a Y as a changing over the time. You have lots of, or anything else actually. X and Y could be anything, any data points. And you would like to find out a line such that the distance, the perpendicular distance to the line from your data points will be the minimum. That's what you want. This is why we call this one is minimizing. Minimizing the length of your line together with your data points. That's what it's all about. Okay, now assume that find this kind of a question. Let's go through the question and have a look. Now the question type. Find the least square solution A of AX is equal to B. A is given by this matrix and B is given by this vector. Now A is not a square matrix. We have 3 rows or 2 columns. But when we multiply this matrix with its transpose, you will find a square matrix. Now, if you have the matrix A, as you realize, this is not a multiple of each other. So the columns are linearly independent. So that is this case. Now the theory tells you that if you want to find out the least square solution, take this matrix coefficient matrix, find out its transpose and multiply from the right hand side. So that's what I'm doing here. So A transpose will be 1 minus 1 0 1 1 2 11 3 4, which is the B vector. Multiplying from this side, I will have this vector. So this is the this side. From this side, I have A transpose A as a matrix. So I have 3 rows, 2 rows, 3 columns. I have 3 rows, 2 columns. So multiplication of these two matrices will give me 2 by 2 matrix, which is the square matrix. So what is the equation in that moment? The equation is, sorry about this. Equation here is AX is equal to B. That's exactly what we say. Well, A transpose A is X is equal to B. So we would like to solve this equation. You can apply it to the row operations. You can find the row operations and do it. But in this case, this is an invertible matrix. You can find out the inverse of this matrix and multiply from this side. That will be the inverse of this matrix times this will give you the result. You can do both ways. It doesn't matter. Since this is a 2 by 2 matrix, it is very easy to find out its inverse. I talked about this before, so I'm not going to repeat it. By now, you should be able to know what is the inverse of the 2 by 2 matrix. If not, you must know it anyway. But if you can't see immediately that in this point, you can always use the linear algebra, how to solve the linear system of equations by just applying the row operations, create the augmented matrix, apply the row operations, find the result. You can do so. Okay, in this case, there exists a unique solution because, as I said, the columns are linearly independent, so it would give us a very unique solution. Now, second question that I'm going to work on with you today is a bit different. Now you have 3 points in this question. These 3 points, we have 3 different ways that we are going to approach these 3 points. Now, first, we would like to find a line closest to the 3 points. What is the minimum, what is the best fit line equation given this data in 2-dimensional space? Because you have pairs, 3 points, pairs. So basically the plane that you're talking about. Now, the second part of this question, we will add the origin as a point. We are not saying that this equation, this line equation passes through the origin. That is not the case for the B section. For this part, we are saying that you're adding the origin into your data set. So like P, Q, R, and the origin in your data set. And you're asking a line equation such that that line passes closest to these 4 points in that time. So that is the part B. Part C is saying that find out the line passing through the origin, because the A is equal to 0 in this case, passing through the origin, find out the line equation passing through the origin, which also the best fits for points P, Q, R. Okay. Let's have a look. Now, you have the data, right? You have xi, yi, xi, yi. So basically, we want to figure out this line equation, y is equal to abx. We want yi is equal to a plus bxi. Right? Basically, what I'm making this as a data points, yi, xi. Here I have 3 points, P, Q, R. YI's are always 1 for P, Q, R points. So this is why I have 1, 1, 1 here. So the A is the starting point. We don't know yet, but there's a number. We just would like to point it out. Our aim is to find out A because we want to find out the line equation best fit to these 3 points. Okay, so this is why I have, and the coefficients of A is 1. That's it. B, this is what we would like to find out, but xi changes. For the point B, I have 1 because P is 1, 1. Q is 2, 1. So x2 is 2 and x3 is 3. So this is why I have 3. So I am converting these points into the equation system. In this equation system, A and B are known. That's what we would like to find out. And we have 3 equations, 2 unknowns in this case. So the equation from here, the coefficients will give me the coefficient matrix. So 1, 1, 1, 2, 1, 3. So the coefficients of this will be the matrix A, and the unknowns A, B, and the right-hand side of the equation will be the vector B. So this is exactly a unknown matrix is equal to B. So the equation is exactly what we've done in the first example. In this case, A as a matrix, 1, 1, 1, and this 1, 1, 1 is coming from the coefficients of A. 1, 2, 3 is the coefficients of B, which are the basic the xi's. Right? This is always 1, 1, 1, 1, as you realize in this case. This has nothing to do with these ones. These red ones is the coefficients of A. That's what I'm trying to say here. I think it is clear. If you understand how you pass from here to here, then it should be clear. Now, this equation is exactly the A times AB is equal to Y. Y is the Y matrix. Y vector is 1, 1, 1. Okay, the theory tells us that find out the transpose of the matrix coefficient matrix and multiply this equation. That's what we are doing here. And then calculate it. And then solve the equation for AB. AB is unknown. That's what you want to find out. So that's what we are going to do. So multiply everything with the A transpose. That's A transpose. Multiplying with A, this times this will give you a 3. This times the green ones, 1, 2, 3. So that's 6. That's 1, 2, 3. That's 6. This times this will be 1 plus 4 plus 9. That will give us 14. And A transpose times Y is 1, 1, 1 will give you 3, 6. So this is the equation that we would like to solve. A and B is unknown. Using the augmented matrix, we have this matrix. Applying the row operation, we will be able to find A will be 1 and B will be 0 after the row operations. So y is equal to 1 is the line in the first part of this equation. Now, in the second part of this question, it says that add the origin to the points, to the data set. Then, again, the coefficient of A is 1, xi is equal to 0, yi is equal to 0. That makes the matrix A is 1, 1, 1, 2, 1, 3, 1, 0. This will be the expanding of the data set. Again, the same idea. We will multiply by its transpose to itself, and its transpose with the right-hand side vector. The right-hand side vector will be 1, 2, 3, 0 in this case. Sorry, the right-hand side will be 1, 1, 1, 0, right? Because the P, the Y is YI. y1, y2, y3, y4. And that will give me the vector 3, 6. So the equation system that we would like to solve is in the augmented matrix form, A transpose A and A. So this is that one, and this one is 3, 6. And if you apply the row operations, then you will find the solution A is equal to B is equal to 3 over 10. So in the B part, you will find the line equations in that way. This third part, the C part of this equation, of this question, asks us that find out the best fit for this data to a line passing through the origin. As you see, the part B and part C is different. Part B was saying that adding the origin to the data set. Part C is saying that find the data, find the line that fits with the data best through the origin. Okay, in this case, we have PQR, so data set is still 3. Here our equation, there's no coefficient. Since there is no coefficient, there's no A, there's no coefficient 1, 1, 1 for the matrix A. So the coefficient matrix is 1, 2, 3. And the left-hand side of the equation is 1, 1, 1 Y's. So the coefficient matrix is just a one column vector. And if you multiply this, 1b is equal to b, 2b is equal to 1, 3b is equal to 1. So that's the equation that we would like to solve. In the matrix form, this is the case, and the matrix is 1, 2, 3. Exactly the same logic. We will take the transpose of it and multiply everything with the equation. So transpose of this by itself will give you only one number, which is 14. Transpose of this 1, 2, 3 multiply with the 1, 1, 1 will give you one number, 6. 14b is equal to 6 implies that b is equal to 3 over 7. So y is equal to 3 over 7x. That is an equation. So we have 3 line equations, and we have some points in the two-dimensional space. So this is the situations, right? So PQR really best fits with the first equations that we found. Y is equal to 1. This is a perfect fit because y is equal to 1 line is passing through these 3 points. This is not going to happen in usual life. This is a very specific example. You will always find a line closest to it. In more general case, the line equations is so stiff in some way, you would like to find the curves close to your data set. That's what is happening in general. For the lines, for this, for the part B, this is the line that we found. Y is equal to 3 over 10 plus 3 over 10x is the line that we found in part B. And this is the line that we found in part C. And the fit, the why, what we are, how the theory says, what the theory says is that this yellow line minimizes the distance between P and that PQR. Minimal distance is the perpendicular distance from this point to the line, and from Q to the line, and from P to the line. So you're getting those perpendicular distances and summing up. Those distances are minimum. That minimum distances will give you this line y under that circumstances. Because we had some requirements, we add the point 0 as well. So you're looking at the perpendicular distance from this point to yellow line for the B section as well. So you have this point and this point, and you're looking at this yellow. If you consider if you consider the origin included in your data, as you see, the yellow line is no longer is the best fit for that B section. For the part B, is this yellow one is really the best fit. Yeah. And if you have, if you remove the requirement that the coefficient can be shifted, and if you want your line passing through the zero, but it not necessarily the zero is there, then you will have the perpendicular distance to the green one. So I've put it like that. So this one, this distance here, this distance here, this distance here from the R to R is minimum for this line. I hope this is helps to visualizing what is happening in terms of the data set, in terms of the how we represent what is the best fit for us. And hopefully this will be clear up some of those concepts for you. And thank you very much for watching, and hopefully it is useful for all of you. Thank you.